Welcome back to a video lecture on the centrifugal pump. This is centrifugal pump part 2. So this is your shape 9. So in this video we will see the topics like work done by the centrifugal pump on water, heads of the centrifugal pump, efficiency of the centrifugal pump, multi-stage centrifugal pumps, specific speed of the centrifugal pump. So first topic, work done by the centrifugal pump on water. We will have a diagram at the bottom. So we will calculate the work done of the centrifugal pump by drawing the velocity triangles at the inlet and outlet condition. This is same as the for the turbine. So in the diagram we will have a suction line. This one is the discharge line. So water will enters in the radial direction at here and it leaves at the discharge line. This is a velocity triangle. So this is the inlet velocity. So this is the outlet velocity triangles. So the inlet velocity will have the absolute velocity v1 and will have a relative velocity vr1 and will have a tangential velocity small u1. Similarly we will have at the top outlet velocity triangle. So absolute velocity capital V2, relative velocity vr2 and will have a tangential velocity u2. So these are the velocity triangles at the inlet and outlet conditions. Now we'll see some terms like En, speed of the impeller in the RPM, capital D1, diameter of the impeller at the inlet, small u1, tangential velocity of the impeller at the inlet. We calculated with the pi dn by 60. And capital D2, diameter of the impeller at the outlet, small u1, tangential velocity of the impeller at the outlet, and we'll have a capital V1, absolute velocity of the water at the inlet, VR1, relative velocity of the water at the inlet, and we'll have a alpha and theta angle. Alpha is the angle made by the V1 and the direction of the motion of the vane. Theta angle made by the VR1 and the direction of motion of the vane. Similarly, we'll have a V2, VR2, beta, phi are the correspondent values at the outlet. As the water enters in the radial direction, so angle made by the v1 and the direction of the motion, that is the nothing but alpha, which is having 90 degrees. Here we need to remember will component is 0. We'll see how to calculate the work done of the centrifugal pump. Centrifugal pump is the reverse of the radial inward flow reaction turbine. Uh, Inward flow reaction turbine work done by the water on the runner per second per unit weight of the water striking per second is given by the below equation, where V W1 is the will component and a small u is the tangential component. So we need to calculate the work done of the centrifugal pump. So work done of the centrifugal pump per second per unit weight of the water striking per second is nothing but the negative of the work done in the case of the turbine. So this will be given as below. So similarly we'll have a VW1 U1 minus VW2 U2. Here we'll have will component as 0. So by removing will component we will get this expression. Here we'll have an expression at the per unit weight. We need to remove the per unit weight by multiplying the weight. So by multiplying weight we will get the expression like this. So W is the weight of the water, which is given as a rho gq. So Q is the volume of the water. Q can be written as area into velocity of the flow. So this will be written as area is pi d1 b1 and vf1. So this will be inlet. We can write similarly at the outlet pi d2 b2 and vf2. So where b1 and b2 are the width of the impeller at the inlet and outlet, and vf1 and vf2 are the velocities of the flow at the inlet and problem. So this is the first problem on this video. So the internal and external diameter of the impeller of the centrifugal pump are 200 mm and 400 mm respectively. The pump is running at 1200 rpm. The vane angle of the impeller at the inlet and outlet are 20 degrees and 30 degrees respectively. The water enters the impeller radially and the velocity of the flow is constant. Determine the work done by the impeller per unit weight of the water. So here we need to First write it down the given data. So we'll see the given data. So given data we written, capital D1 is the internal diameter of the impeller, D2 is the at the outlet, and we'll have a speed, and the vane angle at inlet they given 20 degrees, and the vane angle at the outlet also they given 30 degrees, and water enters radially, so that means alpha is 90 degrees and fill component is at the inlet is 0. So we'll have a velocity of the flow at the inlet and outlet are equal. So from this given data we can calculate the tangential velocities at the inlet and outlet conditions. So first we'll calculate the tangential velocity at the inlet condition with the formula small u1 equal to pi d1 n by 60. So by substituting values we will get the tangential velocity at the inlet 12.56 meter per second. Similarly, we will calculate the tangential velocity at the outlet with the same formula. Instead of d1, we will substitute d2 and we will get the 25.13 meter per second. So this is the tangential velocity at the inlet and outlet. So with this data, we can draw the velocity triangles at the inlet and outlet condition. So here the water enters in the radial direction, so we'll have the absolute velocity is equal to the flow velocity at the inlet condition, and we'll have a alpha here, it is 90 degrees, and we'll have a theta is also given. So this is your small u1, this is your relative velocity. At the outlet we know the phi value, that is the vane angle we know. So we need to calculate the remaining values here. So we will see now from the inlet velocity triangle. So with the help of this triangle, so tan theta equal to vf1 by u1. u1 we already know. Okay, then we need to calculate vf1. So vf1 will be calculated with this formula like this, and we'll get the value 4.57 meter per second. So vf1 is equal to vf2, so we'll get the 4.57 vf1 and vf2. Then from the outlet triangle, so we will write tan phi, tan phi, tan phi we will write vf2 by this part, so that is your u2 minus vw2. So vf2 we know, u2 we know, and vw2 we need to calculate. So from that we will get the vw2 17.215 meter per second. Then finally we will calculate the work done by the impeller per kg of water per second is given by the equation 1 by g vw2 u2, because whirl component at the inlet condition is 0. By substituting these all, we will get this value 44.1 Newton meter per Newton. So this is how now we'll see the heads of centrifugal pump. Here we'll have 4 types of heads. First one suction head, second one will have delivery head, third one will have a static head, fourth one will have a manometric head. So suction head we can see, which is from the sump level to the center of the centrifugal pump. So second one will have a delivery head, which is the from the center of centrifugal pump to the delivery pipe. So we will have the static head, which is the combination of the delivery head plus suction head. You will see first one is a suction head, so it is denoted with the HS. So this is already seen what is the suction head, so which is nothing but the height from the center line of the centrifugal pump above the water surface in the tank or the pump from which the water is being lifted. So second one we already seen delivery head, which is this from the center of the centrifugal pump to the water delivery. Okay, then we'll have a static head, which is a combination of the suction head plus delivery head. Then fourth one will have a manometric head. Manometric head is defined as the head against which a centrifugal pump has to work. So it is denoted with the capital H suffix M. So this will be written in 3 types. So first one we can see HM equal to head imparted by the impeller to the water minus losses of the head in the pump. So this will be written VW2 u2 by g minus loss of the head in the impeller and casing. So if losses are 0, we can write simply this term. So second type we can write H, capital HM is total head at the outlet of the pump minus total head at the inlet of the pump. So we can write like Bernoulli's equation. Then third one will have the HM is the combination of suction head, delivery head. So this one is a frictional head loss in the suction pipe. Then this one is a frictional head loss in the delivery pipe plus VD is the velocity of the water in the delivery pipe by 2G. So this is how we'll see the uh, heads of the centrifugal pump. Efficiency of the centrifugal pump. So here we'll have three types of efficiency are there. First one is the manometric efficiency, which is written as eta suffix man, and mechanical efficiency eta suffix m, overall efficiency eta suffix o. So first we'll see the manometric efficiency. Manometric efficiency is the ratio of the power given to the water at the outlet of the pump to the power available at the impeller. So we can write power given to the water at the outlet of the pump is written as weight of the water lifted, that is W, into manometric head by 1000 kilowatt. Similarly, we can write power at the impeller, which is given as a work done by the impeller per second by 1000. So we'll write W by G into VW2U2 by 1000 kilowatts. So by substituting these one, we'll get manometric efficiency G capital HM by VW2 into U2. So this can be simply written as manometric efficiency equal to manometric head by head imparted by the impeller to the water. So this is written like this. Second one will have mechanical efficiency. Mechanical efficiency is the ratio of power at the impeller by the power at the shaft. So we know power at the impeller can be written like this: W by G into VW2 U2 by 1000. So power at the shaft, which is written as a shaft power. So we'll write the expression mechanical efficiency like this. So S dot P stands for shaft power. So third one will have a overall efficiency. Overall efficiency is the ratio of power available at the output of the pump to the power at the input of the pump. So power output of the pump, this can be written as the weight of the water lifted into manometric head by 1000. So similarly we can write power available at the input is nothing but our shaft power. So by substituting these values, we can write WH suffix m by 1000 into shaft power. So this will be simplified as manometric efficiency into mechanical efficiency. Therefore, we can say that overall efficiency of the pump is nothing but the product of the manometric efficiency. And so we'll have another problem. So this is for your self assessment. So here we will have a extra term, that is a manometric efficiency. With the help of manometric efficiency, you need to calculate these four terms. So here with the help of manometric efficiency, we will calculate the component at the outlet. With this, you will calculate the VF2 and V2 value and beta value, and finally we will calculate the discharge value. See the multi-stage centrifugal pumps. If two or more impellers are connected, then we call it as a multi-stage centrifugal pump. So these pumps may be, or impellers may be connected in the same shaft or different shaft. The main function of the multi-stage centrifugal pump is, first one is to produce high head, second one is to discharge a large quantity of liquid. So if the high head is produced, then the impellers are connected in a same shaft. If large quantity of water or liquid is discharged, the pumps are connected in a parallel. So we'll see one by one. So first one will have a two-stage pumps with a impeller in series. So this is the first impeller, this is the second impeller. So here first impeller output is connected into the second impeller input. So here we will calculate the total head, which is small n. N is the number of identical impellers mounted on the same shaft. So this is the manometric head of the each impeller. So the discharge from the each impeller is same. So second one will have a pumps in parallel. So we'll have a pump 1, pump 2. These two pumps discharges are connected at this point. Here we'll calculate the total discharge, which is small n number of identical pumps arranged in parallel, and Q is the discharge from the one pump. Speed of the centrifugal pump, which is denoted by capital N suffix S. So specific speed of centrifugal pump is defined as the speed of the geometrical similar pump which would deliver the 1 cubic meter of the liquid per second against a head of 1 meter. So we will derive the expression for Ns with the help of discharge expression. We know the Q equal to area into velocity of the flow. Area can be written as pi d into b. Velocity of the flow can be written as v suffix f. So pi is a constant value. So removing equality, we can write proportionality Q proportional to d into b into vf. So b is proportional to d, so we'll replace d with b, so we'll get a q proportional to d square into vf. So you know u equal to pi dn by 60. Pi by 60 is a constant. By removing this one, you will write proportionality u proportional to dn. So we also know u is proportional to vf, which is proportional to root hm. So we can replace u with the root hm. So I can write root hm proportional to dn. In that we can write d equal proportional to root hm by n. So we'll substitute these all terms in q proportional to d square into vf. We know d equal d proportional to root hm by n. By substituting it here, we will get hm by n square into vf. So vf is already known, which is root h. By substituting this one, we will get hm 3 by 2 by n square. So we'll remove the proportionality, we'll get a constant term here. So we need to write the expression for the specific speed. So specific speed is nothing but the when we'll have a 1 meter of head and 1 meter cube per second discharge. We'll substitute these expressions in this equation where n then become ns. So we'll get the constant value k equal to ns square. We'll substitute this k value at here. We will get the expression q ns square hm 3 by 2 by n square. So we'll write in terms of ns. So this is the final expression, n into root q by hm by 3 by 4. So now we come to the end of the lecture. So thank you for listening.